Here's the second half of section 10.5. This one is on what's called dependent events. So we have a definition up first. Two events are dependent if the occurrence of one affects the occurrence of the other. This is called a conditional probability. The probability that B will occur after A has already happened. The easiest example I can give you for something like this would be dealing with picking a card out of a deck. If I choose one card and stick it in my pocket and then I choose another card, I no longer have 52 cards in the deck, I'm down to 51. So the probability of drawing a particular card the second time is now different because I chose one card and I kept it in my pocket versus choosing a card, looking at it, and putting it back in the deck. So anytime you're going to do two events and the second event is totally affected by what happened the first time, that's called a dependent probability. We have a formula for that, and we have to talk about the notation first of all. Here's the notation we're going to look at for a dependent event. P parenthesis B, and then we've got this bar right here. This bar, we're going to use the words given that. So this notation right here, this bar, is going to be read like you read it. It's going to be read with the words given that. What's the probability that B will happen given that A has already occurred? You also might hear the phrase such that. What's the probability that B will happen such that A has already occurred? Your formula for this dependent event is right here. P, A and B is equal to probability of A times the probability that B will happen given that A has already occurred. Here's the word and again means we need to multiply our two probabilities together. And remember, when we're doing regular probability, we're thinking the words yes over total. And then for this second one, the probability that B will happen, we're going to have a yes number for B, but now we know that A has already occurred. We have a new total for A in the bottom that we have to worry about. So as I mentioned with those card questions, for instance, if I draw a card out of a deck for the first time, I have 52 in my deck. If I keep that card in my pocket, I have a new total for A when I try to draw my next card. I'm down to 51 for my total. So whatever the situation is, you're going to have a new total for that second time you try to draw a card. All right, so if you look on example 4 in your book, there's a chart here of some storms that have occurred. So this is example 4 on page 719. We have types of tropical cyclones and where they occurred in the world, whether it's northern hemisphere or southern hemisphere. And the names of these tropical cyclones are either a tropical depression, a tropical storm, or a hurricane. And these are the values that they came up with for how many storms occurred of that type in that part of the world. We're going to try to do some probabilities here. So the first one we're going to do is just a basic probability. What's the chance that the probability that you're going to have just a basic hurricane? There's nothing that talks about two events going on or such that something already happened. So this is a basic yes over total question. In other words, how many hurricanes did we have out of our total amount of storms? So first thing you need to do is figure out, if you add all of these together, how many storms do we have total? Hopefully you came up with 1575. So now if I do my hurricane, out of my total, hurricane, I have two of them, northern hemisphere, southern hemisphere. So I just need to add those two numbers together to come up with my hurricane answer, and then it'll be over my total. So this added together, 760 over 1575. And then you would be asked to reduce that. We're just going to move on to the next one. What's the chance that I have a tropical storm in the southern hemisphere? So now we need to look at tropical storm. Tropical storm is here. Southern hemisphere is this number. So what's the chance that I have a tropical storm in the southern hemisphere? 200. And then my total again, 1575. The third one is also just a basic probability question. What's the chance that I have a northern hemisphere tropical depression? Northern hemisphere tropical depression. Right there, northern hemisphere tropical depression. 199 out of my total 1575. Now the next two questions are notation that uses the dependent notation. What's the chance that I have a hurricane knowing that I'm only in the northern hemisphere, or given that I'm only in the northern hemisphere? So if we look at our chart, here's the northern hemisphere. So that is going to be my new total answer, the total of each of these three numbers added together. And I am specifically looking for the hurricanes in the northern hemisphere. So hurricanes is 545, and my new total is what I get when I add 199 plus 398 plus 545. Hopefully you're going to get 1142 for that when you add all of those together. And then the last question that I had here is, what's the probability that we have a tropical depression given that it is in the southern hemisphere? Tropical depression given that it's in the southern hemisphere. Here's tropical depression, and here's southern hemisphere, new total. So I have 18 over whatever I get when I add 200, 215, and 18 together. 433. And then again, each of those fractions would be reduced. Okay, here's an example. I think this one might be example 5 from your book. You're going to pick 2 cards from a deck, and I want to try to figure out the probability 2 different times. What's the probability that I will choose not a heart and then a heart? But the first time I do this, I'm going to do with replacement. That means that I'm going to put the card back in the deck after I look at it. Once I put it back in the deck, then what I'm dealing with is an independent event. The two answers have nothing to do in terms of relying on each other. I pick a card out of a deck, I put it back in. I still have a total of 52 cards in the deck when I choose my second one. This means it's independent. So probability, not heart, and heart will be just the 2 multiplied together. What's the chance that I have not a heart? Put it back in the deck, look at a new one. What's the probability this time that it is a heart? All right, so how many not hearts are in your deck? We know we have 13 hearts, so not a heart would be 39 out of my total of 52. Times by, how many hearts do we have in our deck? 13 out of 52. And then we can do our reducing. Now these numbers reduce. Hopefully you're going to be looking at these enough that they're going to start to be familiar to you. 39 over 52 reduces to 3/4. 13 over 52 reduces to 1/4. So the probability that I choose not a heart and then a heart with replacement is 3 over 16. Now in the second part, we're going to do this again, but this time we will not replace the card. When I do not replace the card, I now have a dependent event. My total is now different the second time I draw the card. So this time, probability not heart and heart will be the probability that I choose the first card and it is not a heart, times by probability that I draw a heart given that I already drew not a heart. So I have a new total on my second fraction there. All right, so let's start. Probability of not a heart, we already know that. There's 39 out of the 52 that are not hearts, times by. Now I keep that not heart, I keep that card, put it in my pocket, and now I'm supposed to draw a heart. Well, I do know I have 13 hearts in the deck, but I no longer have 52. I'm down to 51 cards. And then I can do my reducing and multiply. 39 over 52 we knew was 3/4. 13 over 51 will not reduce. And now I'll multiply across and across. 39 over 204. And you can always leave your answers in this fraction form. That's perfectly fine. You don't need to switch them into decimals. You don't need to switch them into percents. Fraction answers are just fine here. Next one is dealing with hearts and clubs. So what's the probability that I will draw a heart and then a club, and I'm going to replace the card after I look at the first one, which means probability heart, probability club. How many hearts are in your deck? 13 over 52. I look at that heart, I put it back in the deck. Now I draw a new card. How many clubs are in your deck? 13. Do we still have 52 once I put that card back in the deck? Yes, we do. And how do each of these reduce? 13 over 52 is 1/4. We have another 1/4. Answer 1/16 for my probability. And then we'll do this one again without replacing. So I have probability of a heart is 13 over 52. I keep that heart and put it in my pocket, and now I'm going to draw a club. So the chance that I could draw a club would be 13, but again, we don't have 52 any longer. We're down to 51. 13 over 52 we know reduces to 1/4, and then 13 over 51. And then again, you'll multiply across and across. 13 over 204. This next example is another way that we can use dependent events, and it's by using what's called a tree or a diagram. And this one is example 7 on page 720 in your book. So if you look at the words for the question, using observations made of drivers arriving at certain high school, a study reports that 69% of adults wear a seatbelt while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears the seatbelt, and 26% of the time when the adult does not wear a seatbelt. What is the probability that a high school student in the study wears a seatbelt? All right, so when you start a question like this, we know we're going to be making kind of a tree diagram. So we're going to start on the left-hand side. We're going to start with 2 branches. And each of your branches has to add up to be 100%. So either something happens or it doesn't happen. So if I look at the question again, it says that using observations made of drivers arriving at a certain high school, a study reports that 69% of the adults wear a seatbelt. 69% of the adults wear a seatbelt. So that's the first half of my branch. The other half of my branch will be the people who don't. 69% do. How many are left over? How many do not? 31% don't wear a seatbelt. And this is dealing with just the adults. All right, now we're going to keep reading. And it says that a high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt. Okay, so this is the dependent part of it. 66% of the time, a student wears a seatbelt given that the adult wears a seatbelt. So we're going to branch off of the fact that the adult wears the seatbelt. We're going to branch off for the student. 66% of the time, the student wears a seatbelt. Now remember, every time I make a branch, I have to make sure that those branches add up to be 100. So if 66% do wear the seatbelt, how many do not? The leftovers, 34%, don't wear the seatbelt. And then if I keep reading again, 26% of the time, the student will wear a seatbelt when the adult does not. So even though the adult does not wear the seatbelt, the student may choose to anyway. And that percent again was 26% of the time. 26% of the time, the student will wear a seatbelt, and then the leftover has to come up to be 100%. So what's left over from our 26% is 74%. So now I have my complete tree filled out. Now I can look to see what the question is asking me. What is the probability that a high school student in the study wears a seatbelt? So I'm going to look at this very last column on the right, and I'm going to look for any place where I have the words that say the student wears the seatbelt. Wears the seatbelt here and wears the seatbelt here. But remember, this was a dependent event. They wear the seatbelt when the parent wears the seatbelt. They wear the seatbelt even if the parent doesn't wear the seatbelt. So I need to put these two together. Now remember, these are dependent events, so I need to multiply them together. They wear the seatbelt given that the parent does, 0.69 times 0.66. They wear the seatbelt given that the parent does not, 0.31 times 0.26. I need to come up with these two answers, and the key here is the word or. They wear the seatbelt if the parent does, or they wear a seatbelt when the parent doesn't. And when I have or with probability, I need to add them together. So I'll multiply across this one, get your calculators out, plug that in, multiply across this one, multiply that out with your calculator, and then we'll add them together. And hopefully you come up with your grand total to match what we've got here of 0.536. Or 53.6% of the time, the student will wear a seatbelt in the car. The other example that we're going to do is number 39 on page 723, but this one is in your book, so we're going to do this one in class. We'll hold on to this one. So here is just a reminder again of your formulas. So we're going to go back to section 4. This is if you have one event only. Probability that A or B could happen. Probability of A plus probability of B minus probability of A and B happening at the same time. That's the crossover that might happen. Now, if you have multiple events, this is section 10.5. You need to know the difference between independent or dependent. If they're independent, the two events do not affect the outcomes of each other. Probability of A and B would be probability of A times probability of B. And if it's a dependent event, like drawing a card, putting it in your pocket, drawing a marble out of a bag and keeping the marble, don't put it back in, those would be dependent events. Probability of A and B is probability of A times the probability of B, knowing that A has already happened. And this is the one where you have a new total on the bottom when you do your yes over total. Okay, so that's just a review of your three formulas that we've had lately. Make sure you have all of these on your cheat sheet, and in your notes you'll be referring to them quite often. Okay, that's it for today.